whatever the matrix was that reduced down to this, when you add, of course, what's the row space of a matrix? It's a space spanned by the rows, okay? So whatever this thing had, how many rows does it have? 4, right? Okay, so you know that the dimension of the row space can't be more than 4. Because 4 vectors can't span any more than 4 dimensions. Okay? Could span less, and in this case it does. Because when you add multiples of the rows, you're adding multiples of the vectors. When you add the multiples of the vectors and end up with a 0, that means that there's a C1, C2, C3, C4, such that C1 V1 plus C2 V2 plus C3 V3 plus C4 V4 is 0. Okay? So this happened. This is with the original rows. Row of zeros occurred because there's C1, C2, C3, C4, such that C1 V1 plus C2 V2 plus C3 V3 plus C4 V4 is the 0 vector. Because each of these rows is a linear combination of the original rows. When you add a row to another row, you're forming a linear combination of 2 of the rows. If you multiply by a constant, row by a constant, and add to another, that's a linear combination, right? If you divide or multiply a number, a row by a number, then you just get a multiple of that, okay? It's basically a linear combination of itself, okay? So you think through, and if you interchange 2 rows, well, you haven't changed the set of vectors. It just, V2 goes to V3 and V3 goes to V2, right? You still have the same vector. So this represents a linear combination of all the vectors. So okay, every row is a linear combination of the original vectors. Rows 1, 2, and 3 are linearly independent, clearly. Okay. And I still a little bit to do. Leave it to you, and I'll trust you to make sure you put all this together. Okay. It follows that these rows are basis for the row space. And you can memorize the fact that the rows you get are a basis for the row space. Okay? But you don't really understand it if you just memorize it. Now, so, memorizing it is still, if you remember it and can apply it, it's still a significant thing, okay? But best if you understand why, just understand that all of these are linear combinations of the original rows. And one of those linear combinations gave you 0, so you only have 3 linearly independent vectors. So the dimension of the row space is therefore 3. In other words, if you have a linearly independent subset of a given set of vectors, then the number of vectors is the dimension of the space, because that's how dimension is defined. Or the dimension of the subspace. Okay, the row space. Well, in this case, the row space spans the entire set. Okay. Okay, now what space do these vectors live in? Where do they reside? Well, they're in 1, 2, 3, 4, 5, 6. If you would, well, these vectors each have 6 components. Each vector could be in R6. Okay, so you'd have a 3-dimensional subspace of R6. Now, if you have a 3-dimensional subspace of R6, what's the dimension of all the vectors that aren't in that subspace? You can show me with your fingers. Yeah, it's got to be 3. It's a 6-dimensional space. The original row vectors in their linear combinations occupy a 3-dimensional subspace of a 6-dimensional space. The vectors that don't occupy that row space would span a space of dimension 3. Okay? In that 3-dimensional subspace is your null space. Okay. So you can picture this space. Let's say you've got R6. So here's R6. Okay, well, here's the row space. You know, the way I want to picture this. Just the row space is here and the column space is everything else, okay? Well, not the column space, the null space. Here. Oh, okay. So here's the null space. Here's the row space. The only intersection between the row space and the null space is the zero vector. And since it's in the intersection, I guess I probably ought to put it on the boundary, okay? Because zero vectors in any subspace. It wouldn't be a subspace if it didn't contain the zero vector, because a subspace is a vector space in its own right. And every vector space has to have a zero vector, okay? And the zero vector has to be the same as the zero vector for the entire space. And it's pretty easy to prove that, okay? Okay. Now, column space it contains leading ones, if you want to call it that, okay? Bunch of zeros and then a one. Bunch of zeros and then a one. Okay. Columns 1, 4, and 6 of the original matrix, therefore, span the column space. This is because the column space is the row space of the transpose. And you can put that together, okay? Also, it's because the row operations change the vectors so that the vectors you get here are not a basis of the column space, okay? But they don't change the fact that the first column, the fourth column, and the sixth column are linearly independent, okay? And that the other columns are. Now we want to go on with this picture, but write yourself a couple of notes. Let's see if you're doing that, but kind of lock that in and remind yourself to take a look at this part of the video if you don't totally understand it. Alternatively, dig it out of the book. Make sure you completely understand. You're going to need that for the homework that's due in a while. Let's say it's a function of t from b to w, where b and w are vector spaces. Now, the matrix that we saw earlier would be a perfectly good function from 6-dimensional space to 4-dimensional space. Okay. So the matrix 1, 1, 0, 1, 0. Zero, 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 one, and then it was put 1, 0, 1, not 1, 0. Okay. It multiplies vectors B1 through B6. And yields vectors of length 4, because you got 4 rows here, you get a component, in the product, you get a number for each row. Each row times a column. Well, you know that, you know matrix multiplication since the first day practically. Okay, so that yields vectors of length 4. Maps vectors from R6 into R4. So now we have R6 here. We got the null space. We got the 0 vector. And we got the row space. Okay. That's badly written, just an abbreviation of row space. You want to put just an R there because you might get confused with this R, even though this R's got a fancy extra column, whatever you want to call that thing. Okay, here's your row space. Your transformation takes you over into R4. Makes sense? Okay, now when you go into R4, it doesn't map to all of R4 because, as we just saw, it maps only to a 3-dimensional subspace. Okay. And let's make sure we understand that. Every row here every column here appears over here. So yes, there's a notation. Have a grade freeze on the notation for this thing. Okay. It's the image of the whole space. Anyhow, this thing here is the subset R4. And by the columns of A. And I called it subset, it's actually a subspace. So at this point, I better find my new can of cleaner. I'm going to pause for a second so I can shake the can. You don't have to watch me do that. Although if you want to see. Okay. I call this the subset of R4 stand by the columns of A because every column of A appears over here. Show you how you prove that. Up here in the upper corner. I call it a subset, but you know, you can use stronger language. It's a subspace because a subset spanned by a set of vectors is always a space, a subspace. And again, you should be able to easily prove that, okay? So it's the image of the column space. Now, let's take a look at our original matrix again. Remember, if this is your matrix, then the columns are 1 0 0 0 1 1 0 0 0 1 1 0, right? Okay, those are linearly independent columns, linearly independent vectors. And there are three of them. So they span a subspace, a space of dimension 3. Okay. And they live in R4. They don't live in R6. Okay. So these vectors are in R6, the row vectors, and there's your row space. Okay. These vectors are in R4, and they span the column space. We're going to call that the column space. Now, just briefly, as kind of an aside, why do the columns all appear over here? Well, maybe I better get my picture back again. Well, here's your matrix A. What do you get if you multiply by 1 0 0 0? Multiply this matrix, add 1 0 0 0 here. What do you get? Well, answer is you get this column. You know, this times 1 0 0 0 gives you 1. Any of these others times 1 0 0 0, one's going to be multiplied by zeros, and all the other numbers are going to be multiplied by zeros. And you know, I did something here. Better multiply A by a vector with 6 components, right? We got 6 numbers here. Well, that's column 1 of A, right? Now, let's just stop for a second, make sure we see. Okay, so we can a little trouble seeing this, but you want to understand this, okay? That in order to get the fourth column, we multiply by this vector here, because the one in the fourth column is going to pick out the fourth number in each row. In other words, it's going to articulate with the fourth number of each row to give you the number in that row. Okay? So in the first row, the one is going to be multiplied by that one, you're going to get a one. Second row, the one is going to be multiplied by that one, you're going to get a one. Third row, the zero. Fourth row, the zero will be multiplied by the one. And of course, everything else here is zero, so you're not getting anything else out of these rows. So it gives you this. And then if we want, so that's column 4. And if we want column 6, well, we multiply by 0, 0, 0, 0, 0, 1. Okay. Well, that proves that every column in the column space has to appear over here, because these 3 columns are a basis for the column space. Now, if I multiply by any other vector here, I'm just going to get some linear combination of these. Like if I multiply by two, 4, 6, 0, 0, I'm going to get 2 times this first column, 4 times the second column, 6 times the third column. Okay, and that's got to be in the column space. Now let's do 2, 4, 6, 8, 10. Then I'll have 8 times this column and 10 times this column. Okay. Well, I know that 2 times the first column plus 6 times the second column plus 8 times the third, or 10 times the third column, I think I might have said 8 a minute ago, is a linear combination of the basis of the column space. It's a linear combination, well, it's linear combination of the vectors and the basis of the column space. So it's here. Okay. You want to see that. Helps you understand the structure of these things. So we can understand, for example, with a little bit, how linear regression works. That doesn't look much like linear regression, but we're going to see that. I think we're going to get to that. Okay. So here's a picture. The 0 vector is again over here. So we see that there are 3 important subspaces. We have the null space and the row space of your original matrix. And we have the column space of your original matrix, whatever's left over, which is also space. Okay. T was an unfortunate choice for the name of this transformation, but that's what your text generally uses. I'm going to note that we have an inverse transformation. Which is just the transpose of T. And this space out here is the null space of the transpose. In other words, every vector out here, well, is not in the column space of the transformation. The transpose puts the columns into the rows. So whatever you have out here is not in the row space of the transpose. If it's not in the row space of the transpose, then it's in the null space. Now that takes a little time to sink in, so we'll develop that idea a little more. I need a little more board space. Try to make that a little clearer. But that's okay. Okay. So these are your four basic subspaces. I still forget what you call this. I guess this is the row space of the transpose, but I don't have a good notation for row space. So I'm going to look at see what your book uses real quickly, because I'm simply not remembering. Okay, I can't quickly locate the textbook's notation, but this is what you need to understand these four subspaces. Now you saw these four subspaces in the previous chapter, chapter 5. And they were used because the last section is the section on linear regression. And you use these four subspaces in a way I'll try to address a little bit later, but I want to talk a little bit more about linear transformations. Okay, so again, we've got the linear transformation. And I'll also say, I'm going to just do this for Rn, but it looks exactly the same for any other because any linear transformation can be expressed as a matrix. You know, I might have time to describe how that works, but it's pretty straightforward. It's pretty easy to understand. So I think you get it out of the text if I don't say it here. So we've got like Rn some transformation. I don't want to use T because I want to use the transpose. I'm going to use A that we think of as a matrix. It's a linear transformation defined by a matrix. And we did talk last time about the properties of linear transformation. It's easy to prove that any matrix gives you linear transformation. Basically, linear transformation is any transformation such that when you transform V1 plus V2, you get the transform of V1 plus the transform of V2. Well, it's worth kind of noting that. Okay, so if we've got V1 here, it maps AV1 over here. So we're representing these vectors as points on a, in a blob, but they're points within a subspace. So you can think of three-dimensional subspaces and vectors and so forth if you wish. And if we've got a V2 here, this transforms to a vector A, V2. Now, if you've got a vector V1 plus V2, what does it map to? Well, it maps to exactly what you would expect it to map to, which is AV1 plus AV2. It's obvious if you have a matrix that A times V1 plus V2 equals AV1 plus AV2. Okay. Okay. A little less obvious if AV represents the integral of a function V. Okay. In other words, your vectors are functions, and you've seen examples of that, like C of 0, 1, continuous function to the interval from 0 to 1. Okay. Then the integral is a linear transformation. Because what? The integral of V1 plus V2 is the integral of V1 plus the integral of V2. That's a property of integrals. The integral of F plus G is the integral of F plus the integral of G. Okay? So I'm calling them V1 and V2, but they just be functions F and G. So V1's function F, V2's function G, it works. It's just as linear as anything. Same with the derivative. Derivative of F plus G is the derivative of F plus the derivative of G. Okay? So that's about as weird as they get. Well, no, they get a lot weirder than that, but that's about as weird as anything you're going to see. But once you get used to it, you say, yeah, that's perfectly good definition of a vector space. You've already seen that. And you understand that it has this property, the transformation would have this property of linearity. So that the integral from 0 to 1 could be your transformation. The derivative could be your transformation. And it can all be represented by matrices in a very easy way. I digress and show you how the derivative does, but I want to be sure we get over some other stuff, okay? This picture tells you a lot. And if up here we've got CV1, what's it map to? C times AV1. Okay? And that's very simple to understand. If you got these two things, then you've got it. Okay? Also, the zero vector maps to the zero vector. Now, this zero vector has got n zeros in it. This zero vector has got m zeros in it, but it's the zero vector of its space. Now, it's possible that V1 and V2 could map to the same vector. Okay. Without labeling these things, I got V1 here and V2 here. AV1 equals AV2 is possible. For some transformations, meaning of course, that means that V2 minus V1 is in the null space. I'll comment this is possible. Yep, and only if nullity is greater than 0. Assuming that V1 and V2 are not both equal to 0. And V1 not equal to V2. You could make this a little weaker. You could say that both of these can't be 0, but one of them could. Then technically this statement would work, but that's okay. Okay. Transformation isn't one-to-one. Now, other transformation. The nullity, the dimension of your null space is greater than 0. Then, if you have two vectors in the null space, you have one vector in the null space and one vector outside the null space. Okay. Well, what does this vector map to? So this vector maps to something over here. Okay. Well, let's give these names. Okay, this will be V2. Not in the null space. And this will be V1 in the null space. Okay. Now, let this vector be V1 plus V2. Well, V1 in the null space maps to the zero vector, doesn't? Because it's in the null space. That's what a null space is. V2 maps to AV2. What does V1 plus V2 map to? I'm going to ask you to think about that for a minute. Very quickly got a very good answer. Maps to AV2. Okay. Why is that? Well, let's stop a minute. Let's establish first thing first. Times V1 plus V2 is AV1 plus AV2. Your transformation is linear, in other words. But of course, AV1 is 0 because V1 is in the null space. So AV1 plus V2 equals AV2. You can assume that V1 is not equal to 0. Now, why can we assume that V1 is not equal to 0? Okay, I didn't give you a lot of time to think about that question. But if you ponder it a minute, you say, well, V1 could be non-zero because the nullity is greater than 0, meaning the dimension of this subspace is not 0, meaning you have at least one non-zero vector in it. And probably infinitely many, because you can multiply that vector by any constant. You get another one. So it might just be a one-dimensional subspace, but it ain't a zero-dimensional subspace. There could be any number of dimensions, less than whatever the dimension of this is. This is implicitly Rn, and call this Rn. Okay. So, okay, we assume V1 not equal to 0. Which you can do since the nullity is greater than 0. And V1 plus V2 is distinct from V2. So we got two vectors that go to AV2. Right? So the transformation is not one-to-one. One-to-one means that for every one over here, there's exactly one over here that it comes from. I can say that A isn't 1-to-1. Yeah, just by dumb luck, the camera refocused itself or resumed itself. I'm gonna have to refocus it too, but that came into focus good. Okay, so all that was there, but I made it bigger so it's a little easier to read and write small. Okay, definition of 1-to-1. Let's also call this Z. They call this W because that's pretty standard notation. So if W is a member of W, then there exists exactly one, not on one, vector V in V, such that V equals W. And I actually almost wrote this correctly. I don't know why I didn't. I thought about it. I'm gonna rephrase this. And then I'll explain what was wrong with what I just wrote. That's the idea. But it's not necessary that every vector in W here be the image of a vector in V. Okay? So I'm going to state this differently than the way the book does. The book is going to say if AV1 equals W and AV2 equals W, then V1 equals V2. What I'm going to say is a little more vernacular. I'll say V is the only vector in the vector space V for which this is so. This saying there's no two vectors in V that map onto the same vector in W. That you don't have this. Okay. I mentioned this transformation isn't 1-to-1. That's the case that makes it not 1-to-1. Okay. If for any W and W, there exists a V and V such that AV equals W. I'm sliding back up. Didn't think this. What I said is now under this case where this can't happen, then you say that A is 1-to-1. That's your definition of 1-to-1. It's an okay definition. Your book's definition is a little more formal, but it says the same thing. Okay, if for any W and W, there's just a V such as AB equals W. Transformation is onto. That just means every vector over here is a pre-image over here. Fairly easy concepts, but I remember having to think, okay, what's that mean? Why is that important? And stuff like that, okay? So I assume that at least some of you probably want to think about it too. Okay. Now, let me just take a quick look. See what else I need to talk about. Okay, I'm not going to take time to write this down. But the kernel of a transformation is just a null space. There's your kernel. And the thing at the center. The thing from which you can add any vector to any vector that's not in it and still get something that transforms to the same thing. Okay, among other things. The range of the space, and I don't have a good picture of the range here, so let me come back wherever I did have a good picture of the range. And I can't find a good picture of the range. Oh, there it is. Okay. I've looked at everything but this. Okay. The range would be this. Okay, which we can identify with the column space. The range is everything that you get when you transform all these vectors. Okay, they all live here, and everything here is the image of something over here. Okay, the rank of the transformation is just the rank of the matrix, basically. It's the dimension of your row space. Okay. The nullity is again your dimension of your null space. And maybe there's one other term that I need to. No, I got them all. Okay. So you want to have that terminology, but you're going to read about that, and that's going to be okay. That should be enough to give you a picture of everything, all the important properties and so forth, not all the important examples. You don't need to look at the examples, but this is both in section 1 and section 2, both of which we do by next week. Okay. One of them is due, section 1, I think, is due tomorrow. And some of you already have it done. But if you don't, get caught up. We'll give you a little time to get caught up after the test and stuff. Next time, we'll talk about the linear regression, which I think is one of the neatest things in the course. And it reinforces a lot of these ideas. I didn't assign it at the end of the previous chapter. Even though that's where it is, because you want to establish these ideas first so we can really appreciate it. You got your 4 basic subspaces, okay? Your row space, null space, column space, and the null space of the transpose. Neat stuff.